first slide now. Can you focus? Okay. My colleagues in this work are Bill Targos. Bill Targos is the inventor of the reverse micelle impregnation technique we used at UOP to study this catalyst. Bill Targos also did the scanning transmission electron microscopy work. Michel Cohn did the gas absorption work here. And Hayim Abrevaya, who is now with AIChE, did the AIChE work. This work was funded by the United States Department of Energy, and UOP cost-shared the research. My talk is divided into two sections. The first section, I will be describing the metal particle size effects we see during Fischer-Tropsch synthesis. I will be discussing about two catalysts. One of them is highly dispersed ruthenium on alumina. The second one is intermediate-sized ruthenium particles, 30 to 70 angstrom on alumina. The second part of my talk, I will try to discuss the causes of the particle size effects we see. And I'll be talking about CO dissociation rate differences we see with this catalyst and possible ruthenium oxidation state differences we observe. And if you take ruthenium nitrosyl chloride solution and you impregnate on alumina powder and you then calcine and reduce the catalyst, you end up with a catalyst where you do not see the ruthenium particles in the scanning transmission electron microscope, indicating that the particles are less than 20 angstroms. In fact, according to AIChE, the particle size in this catalyst is about 0.8 nanometer. Now, we're looking at the left side, the same picture, and on the right side, the catalyst after being subject to 12 hours of Fischer-Tropsch synthesis. Now we're seeing some ruthenium particles which have agglomerated to sizes that range between 5 nanometers to 40 nanometers. During this test, we find in the cold product receivers ruthenium carbonyl. We analyze the catalyst before and after the test. We see significant drop in the amount of ruthenium in the catalyst. So what's happening here is highly dispersed ruthenium on alumina forms the volatile ruthenium carbonyl species, and the ruthenium carbonyl gets off from the surface or causes ruthenium migration on the surface. Now, here we're looking at the behavior of highly dispersed ruthenium during Fischer-Tropsch synthesis. This test was conducted at 208 degrees centigrade inlet temperature, 35 atmosphere, 130 space velocity, 2 hydrogen to 1 CO feed ratio in a fixed bed reactor. And here we're looking at a test during the first 12 hours on the stream. The CO plus hydrogen conversion was about 10% during this test. There was about 45 to 50% selectivity to CO2. And the hydrogen to CO usage ratio was about 1. Now, in the absence of water gas shift reaction, the hydrogen to CO usage ratio should be equal to 2. Coupled with the high CO2 selectivity we see in this test, we attribute this to water gas shift reaction being catalyzed subsequent to water gas to Fischer-Tropsch synthesis reaction. We cannot explain the CO2 selectivity by the Woodward reaction. It just doesn't fit the conversion and hydrogen to CO ratios we have obtained in this test. The catalyst has very low olefin to paraffin ratio, and we suggest that the low olefin to paraffin ratio and the water gas shift activity of this highly dispersed ruthenium catalyst are somehow related. we're suggesting here that the in-situ generation of hydrogen through the water gas shift reaction is causing a low olefin to paraffin ratio during this reaction. This shows the methane selectivity for this in this test, which started about 10% and declined to about 6%. Now, intermediate size ruthenium on alumina behaves significantly differently. And before going to behavior of intermediate size ruthenium on alumina, I would like to describe to you how these catalysts were made. Now, here we're looking at the aqueous solution of ruthenium nitrosyl chloride and normal hexane. These two solutions do not mix with each other unless you use a surfactant that lowers the interfacial tension between the two phases. When we mix the three together, we make a reverse micelle solution, and in a certain composition diagram, in a certain region of this composition diagram, we form reverse micelles, which are water cores surrounded by surfactant molecules in an organic continuum. The surfactant molecules orient their hydrophilic portion toward the inside of the water core where ruthenium is dissolved, and their hydrophobic portion toward the outside, the organic continuum. This shows the ruthenium nitrosyl chloride reverse micelle solution. Now, we characterize this reverse micelle solution by small angle X-ray scattering, because the water cores scatter the X-ray differently than the organic medium. We were able to measure the size of the scattering centers. Assuming spherical shape, we have the most probable distribution of this reverse micelle water cores around 70 angstrom. Now, we take the reverse micelle solution, and this is the alumina powder we use for impregnating the reverse micelle solution. After impregnation, the reverse micelles sit on the surface, and you need an air calcination step to burn the surfactant and to form ruthenium oxide, and a hydrogen reduction step to make the metallic ruthenium on the alumina surface. Here we're looking at the STEM micrograph of the reverse micelle-derived catalyst, and in this catalyst, 90% of the ruthenium particles were 30 to 70 angstrom in size. Now, when we test this catalyst during Fischer-Tropsch, we do not see ruthenium agglomeration. We see very mild ruthenium agglomeration. We start with 30 to 70 angstrom ruthenium particle size, and we end up with 40 to 70 angstrom ruthenium particle size. When we start with a catalyst which has 40 to 60 angstrom particle size, and as I discussed yesterday, we test for 700 hours, and the particle size remains 40 to 60 angstroms. So it appears that there is a threshold of particle size as far as migration during Fischer-Tropsch synthesis goes, under the conditions we tested. Now, this slide indicates that when you have ruthenium in highly dispersed forms, ruthenium forms the volatile ruthenium carbonyl species, which causes ruthenium migration, which causes agglomeration and ruthenium loss from the catalyst. And when ruthenium is in the form of 40 angstrom particles, this doesn't occur. We do not see ruthenium carbonyl formation. This slide compares the behavior of highly dispersed ruthenium catalysts with intermediate sized ruthenium particle catalysts. The blue data is the highly dispersed ruthenium catalyst data I previously showed. Now, the 30-70 angstrom ruthenium catalyst has twice the conversion at the same loading. This indicates that the turnover frequency is significantly higher with the 30-70 angstrom ruthenium particle catalyst, which is of no surprise. The CO2 selectivity is essentially zero with this catalyst, and the hydrogen to CO usage ratio is 2, which indicates clearly that this catalyst does not exhibit water gas shift activity. The propylene to propane ratio is about 1.2, significantly higher than what we see with the highly dispersed catalyst. And this supports our hypothesis that in the absence of hydrogen generation through the water gas shift reaction, you can obtain an olefin to paraffin ratio of about 1 with this catalyst. Now the methane selectivity is significantly lower with the intermediate size ruthenium particle catalyst. Lower methane selectivity implies higher chain growth probability in this reaction. This slide summarizes the phenomena we observed so far. Highly dispersed ruthenium, its structure is not stable during Fischer-Tropsch synthesis. It forms a ruthenium carbonyl species and it agglomerates. Intermediate size ruthenium does not do that. Highly dispersed ruthenium has low Fischer-Tropsch activity relative to intermediate size ruthenium, 30-70 angstrom. Highly dispersed ruthenium on alumina catalyzed the water gas shift reaction. Intermediate size ruthenium catalyst did not. The olefinicity was low and the chain growth probability was low relative to intermediate size ruthenium particles with highly dispersed ruthenium catalyst. Now in the second part of my talk, I will show you results from our work where we try to understand why these particle size effects occur. And I will first talk about CO dissociation rate differences. Now, we took the reduced catalyst, the highly dispersed and 30-70 angstrom ruthenium catalyst, we re-reduced in hydrogen, cooled in helium, and then under helium flow, we pulsed the catalyst with CO. Each pulse contained about 9% of the total CO required to saturate the highly dispersed ruthenium catalyst. We looked at the products with GCMS specifically for helium, CO, CO2, water, and methane. We calculated the CO dissociation by the amount of CO2 dissolved divided by half the amount of CO adsorbed, based on the Woodward reaction stoichiometry. Now, after the test, we titrated the deposited carbon in the form of CH4, and we found that the CH4 agreed, the amount of CH4 agreed with the amount of CO2 we made, which confirmed that the stoichiometry of the Woodward reaction was what's occurring here. Now, here we're looking at the CO dissociation results with the highly dispersed ruthenium catalyst. On the left scale, I have CO adsorbed. The amplitude of the pulse shows how much CO was adsorbed. And on the right-hand scale, I have a different scale for CO2 dissolved. During the first 6 pulses with the highly dispersed ruthenium catalyst, we are not seeing any CO2 production. After the 8th pulse, an apparent steady-state CO2 production is achieved. And from the amount of CO2 made and CO adsorbed, for this particular catalyst, under these conditions of 1 atmosphere and 200 degrees centigrade, 280 degrees centigrade, we calculate a CO dissociation efficiency of about 5%. Now this shows the same experiment with the 30-70 angstrom ruthenium catalyst. One aspect of this test which was different relative to highly dispersed catalyst is that we started seeing CO2 right from the first pulse. And after the 8th pulse, again an apparent steady state was achieved. From the amount of CO2 made and the amount of CO absorbed, we now calculate a much higher CO dissociation efficiency of about 24%. And these results are summarized here. Different CO dissociation rate efficiencies with 2 catalysts which have different dispersions. One about 100%, the other about 50%. Now, the last item I want to discuss is ruthenium oxidation state differences. Whether the electronic state of ruthenium was different in the highly dispersed case relative to 30-70 angstrom ruthenium particle catalyst. And we have used 2 techniques to characterize the electronic state of ruthenium. The first one was with X-APS, and we did 2 types of measurements with X-APS. We took the highly dispersed ruthenium catalyst and we externally reduced these catalysts were already externally reduced. We transferred the sample to sample holders under hydrogen, and in one case we conducted the excess measurements without in situ treatment, and in the other case we conducted the excess measurements after in situ hydrogen treatment. We knew that this case would result in oxidation of ruthenium despite the measure we took. And here we're looking at comparison of these two tests. Now, in the air-exposed case, we see below the distance of less than 2 angstrom, which is indicative of ruthenium-oxygen coordination. Now, on the other hand, with the reduced catalyst, most of the coordination, we are seeing coordination shells arising from ruthenium-ruthenium interaction. I would like to remind you that we have corrected the Fourier transform data here by phase and amplitude correction, so that the side lobe at less than 2 angstrom distances reflect true coordination distances and not other effects resulting from nonlinearities in the phase shift function of the Fourier transform. We are seeing as in the fully reduced case for the highly dispersed catalyst, it is the catalyst which was in situ pre-treated with hydrogen prior to excess measurement, there is a side lobe at distances less than 2 angstrom which may be indicative of the ruthenium-oxygen coordination. However, we have analyzed this data further, and our tentative conclusion now is that this side lobe is a noise in the data and is not indicative of the ruthenium-oxygen coordination. Now, excess did not show ruthenium-oxygen coordination for the highly dispersed catalyst. The other set of experiments we did was we tried to, now in excess we probed the S electrons of the ruthenium, highly dispersed ruthenium. With X-ray photoelectron spectroscopy, we probed the P electrons of the ruthenium, and we compared the electronic state of the ruthenium by using X-ray photoelectron spectroscopy. Now, the two catalysts that we're looking at were in situ reduced and then analyzed by XPS in the same chamber. Now, the ruthenium binding energy for the highly dispersed case has shifted by 0.7 electron volt to high binding energy. This could result from electronic state differences between highly dispersed ruthenium and 30 to 70 angstrom ruthenium particles. We understand that there are some other ways of explaining the binding energy shifts during XPS experiments, which are called so-called after state effects. And we're trying to understand which one is valid for our case. Now, let me summarize my presentation. According to excess measurements, there was no obvious presence of oxygen in the coordination environment of ruthenium. According to XPS, we see a higher binding energy for ruthenium in the highly dispersed case on aluminum. Higher binding energy may be interpreted as electron deficiency or slightly positive oxidation state for ruthenium when it's highly dispersed on aluminum. Now, regardless of whether ruthenium is in slightly positive oxidation state when it's highly dispersed, we know that if for small particles there will be fewer available ensembles for dissociating CO. Ineffectiveness for CO dissociation has several implications. You enhance formation of reactions which do not require CO dissociation, and these are ruthenium carbonate formation, and it implies low chain growth probability, because if you cannot dissociate CO, you have low concentration of CH2 groups relative to hydrogen on the surface, which results in low chain growth probability. If you cannot dissociate CO effectively, you have low Fischer-Tropsch activity and the reaction which does not require CO dissociation, which is water-gas shift, is enhanced. Now, if indeed ruthenium is in a slightly positive oxidation state, like as the XPS experiment suggests, then this would also imply that CO would be ineffective for, the highly dispersed ruthenium would be ineffective for CO dissociation, because CO dissociation requires electron-rich metals. Slightly positive oxidation state would imply also that water dissociation is enhanced. Ineffectiveness for CO dissociation and effectiveness for water dissociation would show why high water gas shift activity is obtained with highly dispersed ruthenium, but not with 3070 axiom ruthenium particles on aluminum, which are metallic in character, do not form ruthenium carbonyl, have high chamber permeability, high Fischer-Tropsch activity. Thank you very much for your attention.
Papers open to Alex.
Yeah, one of the easy ways to look for highly dispersed ruthenium and to tell whether it's neutral or positively oxidized is positively charged is to do CO chemisorption and then do infrared spectroscopy. On the large particles, you see a single line characteristic of a linear carbonyl. On the very small particles, you see evidence of positive charge, and you see a tricarbonyl. It's a real nice fingerprint.
Yeah, and we have the capability to do that. That's something that we do.
Did you do it on these catalysts?
We did it, yes, we did it on the modified ruthenium catalysts.
Yeah.
But I did not compare two catalysts where we had different particle sizes. But that's definitely something to pursue.
Now, I think that the presence of positively charged ruthenium has been already identified by different methods. For instance, Donner and Mary Good made in situ Mössberg spectroscopy on ruthenium at liquid helium temperature. But you see, which worries me that the formation of a volatile carbonyl species is probably not due to the presence of the positively charged ruthenium, because you see, as Alex told, if you have a positively charged, the more positively charged the ruthenium, the weaker the CO bond is. So in fact, you have to reduce it to metallic state in order to be able to volatilize your cluster.
Yeah, but you can look at it the other way around. If your ruthenium is positively charged and you will not be able to dissociate CO, then you will have reactions, carbonyl formation reaction enhanced.
Okay, so this is what you...
The apolar side of the micelle is just on the outside. Therefore, I can expect that the micelles are being absorbed by the hydrophilic supports.
You said outside?
The outside of the micelles is apolar in the first micelle. You have the polar end of the surfactant on the inside. So therefore, I expect that the micelles will be selectively adsorbed by the hydrophilic support. Nevertheless, you see the adsorption. If you are pouring the organic liquid containing the first micelles over the support, you get an adsorption and you can just drive it away or just...
It's a very quick adsorption. If you start with you start with a colored micelle solution, you mix with your aluminum powder, and it's almost instantaneous removal of the color. So impregnation is very fast. It appears that the surfactant, the nature of the surfactant is very important for this adsorption process.
So all surfactants are maybe right with adsorption behavior?
We haven't studied in detail the nature of the surfactant, but we know for a fact that the nature of the surfactant is very important for the rate of adsorption.
You used the terminology structure sensitivity, I assume in the loose sense here, because it seems in the case of these well-dispersed ruthenium catalysts you have a somewhat of a positive charge, whereas in the other case you have a more metallic nature. And I wonder in the case of these well-dispersed catalysts if that has something to do with a metal support interaction. We're talking about metal support effects rather than differences in metal structure.
I don't think our work was able to distinguish between these two effects. I mean, there are behavior differences, but I don't think we were able to remove the effect of charge at the metal oxide interface from the effect that results of the particle size differences regardless of charge. I don't think we're able to remove these two effects from each other.
The last question prompts me to make a comment and an observation. A few years back, you may recall, we did a study of dispersion effects of ruthenium on aluminum. And as you increase the dispersion, the turnover frequency falls, and it falls along a curve that initially can be described by the change in the proportion of surface atoms that are on flat facets. Beyond 80% dispersion, it falls very rapidly, and that's the region where you start to see large numbers of these positively charged ruthenium centers. So that onset is probably due to the change in charge, the onset of the break, and the more rapid decline in turnover frequency.
Yeah, that may very well be, but again, we have indications that at the metal support interface, the metal may be in a non-zero valency, but we don't have proof for that. I would like to, because XFs, when you probe the S electrons of the ruthenium with XFs, you're not seeing any indication of ruthenium-oxygen coordination. It's predominantly metallic ruthenium. The indications are so far from XPS, and they are not conclusive. So,
The only question I would have, when we enter the fray, is if you actually looked at the number of metal atoms at the edge as compared to the overall sample, whether your XPS would be able to discriminate. You're averaging, your XPS measurement is an average over the entire, both surface as well as the some degree of depth penetration. If you only have different oxidation state at the periphery, thank you very much. And the next